So this is an example of solution stoichiometry. And in solution stoichiometry, instead of giving masses of compounds that react, you're going to be given solutions of certain volume and of a certain molarity, and they're going to react usually to produce a precipitate of some sort. They can be a limiting reagent problem. I'm going to keep that aspect of this relatively simple. And then you can be asked, how many moles of precipitate there are, how many grams of precipitate, what's the concentration of all the other ions at the end, including the spectator ions. And the critical thing here really is to get to moles and think of molarities as sort of branches off of that. So imagine you have a situation. You have two solutions. You have a solution of sodium sulfate, and it's going to be mixed with PbNO3. That's lead 2 nitrate. And lead sulfate is going to precipitate out. We know we're going to end up getting PbSO4 solid, plus the ions. They're going to also get the Na and the NO3 are going to be hanging out saying AQ. The reality is, when you're done with this process, you basically have a net ionic reaction of Pb2 plus SO4 2 minus to give you PbSO4. This problem is inherently easy because the coefficients are all 1. Now imagine what we're mixing as follows. We have 1.25 liters of 0.0500 molar PbNO3 and we're mixing that with 2.00 liters of 0.0250 molar Na2SO4. Now, the good thing in this particular case is, because there's only one lead here and one sulfate here, the molarity of the compound will be the same as the molarity of the lead ions and the molarity of the sulfate ions. That does not necessarily need to be the case. And you can see how if there were two leads in one thing and one sulfate in the other, that would throw things off. So you really need to know the concentration of the ions. Good thing in this case is, when this disassociates, it gives you 1 Pb, even though it gives you 2 nitrates, which I really don't care about because they're spectators, right? And this gives you just, it gigives you 2 sodiums, 1 plus, sorry about that. It only gives you 1 sulfate, which means if we know the concentration of lead nitrate, we know the concentration of lead and vice versa. But you should be aware it doesn't have to be that case. So if we multiply these guys out, right, which I'm going to not even do the math here, we just multiply those two numbers, we get basically 0.0625 moles of Pb2 plus, and we get 0.0500 mole of sulfates. We're really just using this reaction here, and we have a very, very simple limiting reagent problem because it's a 1-to-1 ratio. You honestly don't even have to write this out. You can just basically explain which is your limiter. If all 0.005 moles of sulfate are consumed, you're going to consume 0.05 moles of lead because it's a 1-to-1 ratio. So basically, you're going to consume, 0.0500 mole of the Pb2 pluses, leaving some lead behind, because this is your limiter. And this number here is in excess. Now, for this, if I was doing this in AP, I'd say, well, because, Pb2 plus and the sulfate react minus in a 1-to-1 ratio, 0.0500 mole of SO4 2 minus will react with 0.0500 mole of Pb2 plus, leaving 0.0125 mole Pb2 plus in excess. We can then, if we want, we can write down what the mass of the precipitate is if it's asking for. So if it asks for the mass of the precipitate, because this is a 1-to-1 ratio, right, we know we're going to get 0.0500 mole of PbSO4. And we would even say that, right? We also know that we're going to make exactly 0.0500 moles of PbSO4 because there's a 1:1:1 ratio of lead to lead sulfate. And again, we have to use that ratio. So if it's not 1:1:1, we'd have to do a little bit of math. So if for every 1 mole of, let's say, Pb2 plus, you made 2 moles of something, you have to multiply by 2. You don't have to do this in this particular case. However, you do want the mass, so you're going to do usually a very simple factor label problem. For every 1 mole of PbSO4, that weighs 303.3 grams. This says 3 sig figs. This one has 4, so I'm going to round to 3 significant digits, and my answer is 15.2 grams of PbSO4 will be what precipitates out. Now, what they'll often ask you is to draw a picture of what remains in the beaker at the end, or they'll ask you to determine what the concentrations of the ions that are remaining in the solution are. And this means you're going to have to figure out how many moles you have of everything. So I'm going to turn to the next page and write some information down, and we'll talk about that next. So what I've done here is I've written down some basic information we started off with. We started off with 0.0625 moles of PbNO3, lead 2 nitrate. We started out with this many moles of sodium sulfate. We know that by multiplying the molarity times the volume, we can get the moles of those things. If they ask you ever, okay, well, what is the concentration of all the ions in the beaker at the end? Well, we know at the bottom of this thing we have a bunch of PbSO4. And we know, since the sulfates were the limiting reagent, that there's no sulfates up here in this beaker. They're all down here at the bottom. They're all solid now, right? Well, what is the concentration of everything else at the end of this? Well, the critical thing is this. We combined 1.25 liters and we added to it 2.00 liters. So our final volume here, right in the mark here, is going to be 3.25 liters. That's the volume of our solution. Well, what's the concentration of the ions? Well, concentration is the moles per liter of solution. We can't just take the original molarities. We actually have to figure out how many moles were of these individual ions when we're done with the reaction and put them over the total volume. Well, for the lead ions, it's pretty easy because we know we have 0.0125 moles of Pb2 plus remaining. We simply put that over the 3.25 liters, and that's going to give us the concentration or molarity of the lead ions in the solution, like an idea of what's floating around in there. Okay? For the nitrates, however, that gets a little more complicated. Because in the case of the nitrates, for every 1 mole of lead nitrate, there's 2 moles of nitrate. So in this particular case, you kind of got to go like this. For every 1 mole of this stuff, the PbNO3, there's 2 nitrates. And that's really just a simple idea, which means we basically have 0.125 moles of nitrates just floating around in there, and they're now in 3.25 liters of solution. So that's our volume, and that's going to give us the molarity of the nitrates. And what you want to realize is right off the bat, if I were to draw this in diagrammatic form, there should be 10 times more nitrates than there are leads. Okay? And the final thing that you have going on over here is this. And you have the same sort of situation, right? You start off with 0.0500 moles of sodium sulfate, but for every 1 mole of this stuff, the sodium sulfate, there's 2 moles of Na pluses. Now I can do that one in my head. That's 0.100 mole of sodium ions. And again, that's going to be over 3.25 liters. So I can figure out the molarity, or the concentration of each of the ions at the end. And what you want to notice is because it's a larger volume, the molarity is actually going to drop with respect to the nitrates and sodiums compared to what it was originally, although we never bothered calculating that at the beginning. So what you finally get is you have this is a molarity of your sodium ion this is your sodium ion concentration, this is your nitrate concentration, and this is the lead concentration. And the reason why there's not very much of this Pb2 plus left in here, and there's a lot more of the other ones, is because a lot of the lead was consumed, because that was your excess reagent, and a lot of the lead ended up down here as a solid precipitate on the bottom of the beaker.